Now that we've talked about dimension, we're going to talk about a very closely related concept of rank. They're so closely related that I'm combining the two into one homework assignment. But let's just take a quick recap of some of the things we know so far, and we'll use that as an example to move forward into this idea of rank. So let's start with this 3x4 matrix here, which row reduces to this thing over here. And having that row reduced version, we can say some things about the bases for the column space and for the null space. We know where the pivot positions are. We've got a pivot right there and right there, so there are two pivot positions. Means we could immediately write down a basis for the null space, or sorry, a basis for the column space. So basis for the column space of A would be 1, 3, 0. And 4, 3, 1. And again, keep in mind the reduced version of the matrix, you can't use those two columns as a basis for the column space. 1, 0, 0 and 0, 1, 0 don't produce everything that these two over here do, particularly these two miss the third entry in the vector, which apparently can be non-zero. Anyway, there's the basis for the column space. And knowing that, we do know the dimension of the column space of A is 2. Because of that, we automatically know the dimension of the null space of A is also 2, because there's 4 columns total, so that means there's going to be 2 free variables, and those free variables will determine the basis for the null space. So we know the dimension of the null space of A is also 2. Actually, finding that basis for the null space is a little bit more work, but we sort of just imagine that there was, this row of zeros on here that we were trying to produce, and we would rewrite the equation something like x1 equals -2, x3 x2 equals -4 x4, oops, x4 down there, not an exponent. And x3 and x4 are the free variables. So when you break this down, the dimension of the null space basis, let's see, it's -2, 0, 1, 0 times x3 plus 0, -4, 0, 1 times x4. That's the full null space, but therefore the basis for the null space of A is those two R4 vectors. Okay, fine. All well and good. I want to introduce to you a third vector space that this same matrix produces. We've already got the column space. We've already got the null space. What else could there possibly be? There's this little thing called the row space. Figure with column space there must be a row space as well, and there is. Maybe we should define this first. So let's just say the row space is the vector space produced by linear combinations of the rows instead of the columns, which would be the column space. Another way to say the row space is this the column space of A transpose. If you transpose this matrix, then rows become columns, of course, and the column space of the transpose would be the same thing. But either way, we are talking about the linear combinations of 1, 4, 2, 1, 3, 3, 1, 2, 0, 1, 0, 4. Those three vectors. And it turns out we're going to ask these same sort of questions, like what's a basis for the row space of A, and I guess we could, once we know that, we'll know the dimension of the row space of A. It turns out the basis for the row space is any row with a pivot. So let's unpack that a little bit. Basically, we're looking for the linearly independent rows. And we want to remove any linearly dependent rows. So how do you know if a row is linearly dependent? Apparently you can use the other rows, some combination of the other rows, to make this one. And look at what happened with the third row. It became 0, 0, 0, 0. You know how we did that? We didn't actually do it, but think about what it would have to have been. It would have to be some combination of row 1 plus some combination of row 2 that zeroed out row 3. So row 3 is apparently some combination of row 1 and row 2. So row 3 is the linearly dependent one. It's the one that became all zeros. And the basis for the row space is the first two rows. Oddly enough, unlike the column space, you can actually use the first two rows of the original, or you can use the first two rows of the reduced one. Either one of those would make a basis for the row space. Hopefully that makes a little bit of sense, because what we have here in the reduced version is just linear combinations of the original two. So they're still going in the same directions that these two were, and they're still linearly independent. So the basis for row A could be 1, 4, 2, 1 and 3, 3, 1, 2. Or it could be 1, 0, 2, 0 and 0, 1, 0, 4. And it's sort of traditional to write rows in row notation. You could certainly flop them over vertically and write them like columns if you wanted to, if that's more convenient for some reason. So those are the basis for the row space. The dimension of the row space is 2. So there's the definition of a row space. The basis of the row space. It's just those non-zero rows, the ones that are linearly independent. Oops, so non-zero rows of the reduced version of A. Which, by the way, every one of those has a pivot in it. So the number of pivots gives both the dimension of the row space, and it also gives the dimension of the column space. So that's theorem 13, first of all. It's just that if two matrices are row equivalent, they have the same row space. So whatever row space is for this one over here is the same as this one over here. And the non-zero rows of B can be a basis for the row space just like the non-zero rows of A. Okay, and it probably is worth defining the word now, rank. So that's what 4.6 is about, rank. Rank is the dimension of the column space of A. That's all it is. We could have defined it in the last section. Rank is 2 in this example, but let's point out here that rank is both the dimension of the column space and the dimension of the row space. Those are always the same. However many pivots you have produces pivot columns, and it also identifies the linearly independent rows. So rank, column space of A, dimension of the column space of A, and dimension row space of A, because those are the same thing. So we know that the dimension of the column space is those pivot columns, and the dimension of the null space is those free variable columns. We already said the dimension of the column space plus the dimension of the null space has to equal the number of columns. So here they're kind of just rewriting that and calling it the rank theorem. Hey, look, we get a theorem out of this practically for free. It's something we already know, but just we can use our new words on it. So instead of saying dimension of the column space of A, we can say the rank of A plus the dimension of the null space of A equals n, the number of columns. Okay, so let's get another example out of this. I know there's a lot of kind of new vocab and ideas floating around here that are really old ideas, but they feel like new ideas just because of the new vocabulary, I think. Speaking of new vocabulary, let's lock this down first, and then maybe we'll go into another example. This is all the way back from 2.3, the invertible matrix theorem. Remember this guy? There was like A through L, and I promised that there were more coming. This is about the square matrix, so being invertible, reducing to the identity matrix, having n positions, having the null space be only the zero vector. Except we didn't use those words. Guess what? That might be another statement. Anyway, let's look at continuing the invertible matrix theorem. In the last couple sections, we've gotten some more vocabulary. So if there's a pivot in every column for a square matrix for a 3x3 or a 5x5, having 3 pivots or 5 pivots, that does mean you've got a basis for R3. You've got 3 linearly independent vectors, or basis for R5, which means that the column space is all of R3 or R5, whatever you are. It means the dimension of the column space is n. Or, to use different words, dimension of the column space literally is the rank, so it also means the rank is n. Which means they really could have said dimension of row space of A is also n. Also, the null space has only the zero vector in it, which means, again, if there's a pivot in every column, the only possible null space vector is the null vector, the zero vector. And it means the dimension of the null space is 0. All right, so we've got, like, I don't know what A through R is. Is that like 17 different statements in the invertible matrix theorem? And there's a few more to come. So that's it for the concepts of rank. I think I'll do another example or two in the next video.